Everybody, welcome and thank you so much for joining. This is the Future Leaders in Robotics and AI seminar series brought to you by the Maryland Robotics Center at the University of Maryland. This series is really intended to promote our up-and-coming early career researchers in robotics and AI. I encourage all of you to attend, to go to the robotics.umd.edu/futureleaders to see the full slate of presenters that we have this semester, as well as presentation recordings from previous semesters. Also, to have the opportunity to nominate somebody for next year. We have two presentations going on today. The way that this is going to work is that we're going to have 30-minute presentation from one speaker, and then at 2:30 we're going to have our next presentation. And so it's my distinct pleasure to introduce to you our first presenter of the day. Reuth Mirsky is an assistant professor in computer science department at Tufts University. Before her current position, she was a senior lecturer at Bar-Ilan University and a postdoc at the University of Texas at Austin. She received her PhD on plant recognition in real-world environments from the Department of Software Information Systems Engineering at Ben-Gurion University. Her research focuses on multi-agent systems in human-robot interactions, especially the agency required from a good teammate. Reuth served as a program co-chair, diversity and inclusion chair, or co-chair for various international gatherings in HRI, AI, and planning. She has also organized multiple workshops and events at prestigious conferences in robotics and AI, such as the AAAI, AAMAS, IROS, ICRA, and HRI. And so without further ado, we're going to swap our presentation and let Reuth take it away.
Thank you, Yancy. Let me share my screen. Can you see it okay? Awesome. Okay, terrific. Thank you so much for having me today. I'm very excited to be part of this series. I'm very excited to tell you today about the research I've been doing for the past couple of years about the agency of our artificial teammates and how should we look at our robots around us. So I want to start with discussing a bit what do we mean when we say that a robot behaves well? What is a good robot in our eyes? And traditionally, these discussions highlight the importance of safety, and recent work has refined this notion even further. And the things we usually talk about beyond safety are that a good robot should be able to understand what we want from it and should be able to act in ways that we will understand. And it should also be aware of its own resources and how to use them efficiently. And a very important assumption that these works make is that a good AI agent should also be compliant and will act, or at least try to act, as it was instructed under the safety constraints it was given. So in my research, I argue that this compliance is not always desired, and I take inspiration from guide dogs for this. These are dogs that are trained to lead visually impaired and blind people around obstacles, and they're unique in being the only service dogs that are not just trained on obeying their owner, but also on intelligent disobedience, which means that if they are given an unsafe cue from their handler, they are taught to disobey it. So, for example, if a person wishes to cross a busy street, but a car is coming or approaching fast, the robot knows it should disobey even if the person insists on crossing. And this understanding makes them a very intelligent collaborators for us, because the dog who usually does obey, if you're familiar with Labradors, Retrievers, they are really compassionate. They're really trying to please their owners. And they understand both a context and a state that are so unsafe that they should not obey their owner or even force action on them. So in my research, I'm interested in these types of questions. Can we design and build AIs and robots with intelligent disobedience? And especially, can we design a guide robot that can intelligently disobey instructions? So in my research, I explore what does it take to design an AI system or a robot that is able to perform intelligent disobedience. So if you consider a visually impaired person that wishes to cross the road, an important global objective in this situation is the safety of the handler. However, the handler also has some local objectives in this scenario, which is to reach some destination goal, like reaching my university or going back home. And there might be more than one crossings nearby, which means that there might be different plans to reach that goal. So the robot should also be able to perform plan recognition to disambiguate between these different ways of reaching my objectives. So in this case of the person crossing the street, the command that it would give the robot is hop up, which means move on forward. So in that point, the robot should perform a consistency check to find out that if it moves fast as requested, there will be some conflict with the global safety objective. So at this point, the robot should already understand that and should be certain enough that it should override the hop up command. But then it should reason about how to do that. So mediation is the last part of it. It might just be stopping and waiting for the environment to change for the car to pass them. Or it could be offering alternative plans. For example, there's a traffic light nearby, which is safer. Do you want us to go and cross the street there? So today I'm going to talk about three parts of this. Like, it's a very large, ambitious project with a wide, broad vision. I'm going to talk about three specific works that are that I've been exploring in this area. So the first one is goal recognition and reinforcement learning. So goal recognition is a very useful task that people and agents use a lot in multi-agent systems. If we talk about autonomous vehicles, understanding other cars around us, having service robots being able to properly identify the desires of clients, a surgical robot understanding when a physician may be deviating from a guideline, even for adversarial reasoning, when we have attacks, to be able to intercept them, we need to understand the plan of our adversaries. And even if we want it just as a hobby to jam with a robot, we want the robot to understand where the music is going to be able to collaborate with us. So all of that requires goal recognition. And it's been defined as a fundamental AI problem. Already in 1986, it was coined by Henry Kotz and James Allen as plan recognition to infer the goal of the agent given a recipe database and observations. And a seminal work on this is Plan Recognition's Planning, in which in 2009, Ramirez and Geffner identified that basically you can use planning to solve this problem. So basically you have the recipe database on the left here, the set of candidates' goals, what can the agent do in the environment. And once you get a sequence of observations, you use planners to imagine if I need to plan with the observations to reach goal 1, 2, and 3, which one makes more sense? And then you understand with planning that for another agent, the reasonable plan would be, for example, in this case, to reach goal number 2. There are many challenges in using this type of approach. Mainly, these domain descriptions in which you explain what can happen in the environment is very costly. It's very susceptible to noise because you can only represent the plan that you identified using your planner. And you need to run these planners online because you are dependent on real-time observations that you get. So in my work, one of the things we did, we took this general pipeline that was traditionally used and we modified it to use reinforcement learning. So in general, what we use here, we have some raw data which is being compiled using activity recognition into a sequence of symbols. In this case, for example, the symbol fry an egg. We have some domain theory, which is the hand-coded description of the environment, our recipe set that we have. And using planners, we understand that this person in the image is making breakfast. What we did in our work, basically, we replaced the domain theory with a set of functions, distributions representing what is more or less likely given each of the goals to observe. And then in real time, we only need to use some measurement to see how similar the trajectory we got is to any of the potential policies or trajectories that we expect, behaviors that we expect the agent to take. So the first phase in this work is to learn how would an agent trying to pursue goal number 1 looks like. And the second part is inferring, given a specific observation set, understanding what is the goal of the agent. So a very quick running example, again, we have the similar set of candidate goals, the domain theory that we are using, and a sequence of observations. At the first phase, we learned a specific policy for each of the goals. What should the agent do at each state? Now, this is very simplistic. Potentially, when you're in the initial state in the blue here, you might also go to the right, and that's still part of an optimal plan. This is only for brevity. This is a very simplified example. But we learned that this is an optimal behavior for reaching goal number 1. This is for goal number 2, and so on. Once we have these policies, once we get the observation sequences, we can just match how many of the observations are likely given this policy. And here it's very clear that goal number 2 is the likely one. And here we didn't have to use any planners online. It was very quick to infer that. So we used a lot of planning-based domains to evaluate this work. We compared 3 variations of goal recognition as Q-learning, which is the most basic approach of goal recognition's reinforcement learning we implemented. We just use 500 training episodes. If you're familiar with reinforcement learning, that's very fast to learn the different policies for different separate goals. And we compared that to plan recognition as planning. We varied the observability levels and the noise that the agents can get. So overall, we had 210 goal recognition problems. I can show you some results that, for example, this is the F score, how accurately we were able to identify goals correctly. And the first 3 are variants of our algorithm, and RG is Ramirez and Geffner is the plan recognition is planning comparison. And you can see that even when we have full observability in all 3 domains, we were able to outperform the state of the art. And that becomes even more apparent when we only have 10% observability, which means we've only seen 1/10 of the plan of the agent acting in the environment, and we were still able to infer correctly the goals of that agent. So that was very impressive. That was a huge win. So we were able to reduce the cost of domain description because we are learning our policies instead of using a manually hand-coded domain. Because we are using a full policy of the environment that we are learning, it is more robust to noise, and it can understand whether a state that is very distant from the optimal plan we've observed is very far or just a little far from optimal. And we don't have any online planner or parser runs that we have to conduct. And a bonus point is that we actually don't need to have perfect policies to have good performance here. We just need the policies to be different enough from one another. So if you take the policy that we've trained for goal A, if you just run it to try and get to goal A, sometimes it won't even reach the goal. It's just good enough to distinguish goal A from goal B. So that was a huge win. That's a bonus point for us, and we were very, very excited about this work. This is something that is still ongoing, so hopefully I'll be able to share more soon. The second project I want to talk about is when to interrupt when we want to get more information. Assuming that there is some discrepancy, some ambiguity, we are unsure what the goal of our agent is. How can we elicit more information? So I look at interruptions as a type of intelligent disobedience. Basically, we are not meeting the team's expectations. No one wants to be interrupted. There is some cost on trust when we are asking for a question. We are interrupting. Someone might feel that a robot that asks too many questions is unreliable, but it can promote team goals. If we are asking the right questions, the robot can actually be a very helpful teammate. So if you consider this robot in a hospital that needs to fetch the right medicine for a physician that's about to visit a patient, if the robot asks which patient are you going to visit, then obviously it will be able to fetch the right medicine. But sometimes it can just infer that from where the physician is going. So when to ask the question and when is an important challenge that we should tackle. So we took this medicine fetching example, and we translated it into the physical world to see how interruptions from a robot will affect a human teammate. And in this example, we had a participant, which you can see here, playing the role of the physician. But instead of going to the patient room, it needed to reach one of 4 potential locations in the room. And each location is defined by a set of 3 shapes. So the participants will need to understand where to go according to these shapes. They also have a secondary memorization task in which they need to memorize a sequence of 10 words of some sort, for example, cities. So when the person reaches the final location, they need to write down these words using a pen that the robot will fetch. So the robot needs to fetch the right pen that matches the station from a pen station on the side. So in order to know if the robot is unsure which pen it should fetch to the person, it needs to interrupt them and ask for a clarification. So in this setup, the participant has a cognitively challenging task. They need to memorize a sequence of words, go to the right location and write down the sequence of words while being interrupted by the robot. So we wanted to see how that would affect the perception of the interaction and the objective performance. So we varied different things we can ask the person. In terms of the query content, we asked, what is your goal station? Or are you going to a station with a circle? Or are you going to station circle square plus? In terms of timing, we wanted to see if there's a difference if we ask the question in the beginning of the trial or in the middle of it. And we used proxemics principles to test the distance, whether the distance between the robot and the person would also affect this interaction. And we used the different zones, personal, social, public zones, to estimate that. We combined all of these parameters together, and so we had 15 different setups. And we ran a within subject design with 30 participants. Each of them experienced all 15 variations with 15 breaks between them, and one control one without any question at all. So we looked both at objectives and subjective metrics of performance. Objectively, we wanted to see in terms of information retrieval, was the person able to recall the sequence of 10 words correctly using precision, accuracy, and recall? And subjectively, we used a system usability questionnaire to ask the person about the robot's perceived helpfulness, level of distraction, and comfort, how comfortable the interaction was. So this was a complicated study, and we could have measured a lot of other things as well that we did not measure. So I can definitely see potential for future studies using this setup, but this was a very interesting first step. And the outcome was interesting. It implies that the way humans perceive the cost of interruption is not true to its objective cost. So both of them should be acknowledged independently. In terms of the objective performance, there was no significant interruption. People actually performed just as well with the robot interrupting or not. We did test that this was challenging enough that other things could have interfered with a person, but the robot asking a question was not significantly interruptive enough. But the way people perceived the interaction was interruptive, and people found the robot to be less helpful and more distracting when it was asking questions, especially when it was asking from 5 meters away, from very far away. So that was an interesting result. And that emphasizes that we should acknowledge and measure both objective and subjective metrics when we are evaluating human-robot interactions. So this is a very interesting line of work, and as I said, it's something that we can still develop to many different directions. Some of this that I will mention is exploring interruptions when we have non-optimal agents. We are assuming that the people around us potentially not acting optimally. We might have more ambiguity in the environment, so we might interfere more or need to interfere more. Understanding the value of information and asking questions in a shared control setting where we have a robot and a person that needs to merge their behaviors together. Or to when we have a teacher robot that tries to teach a person and needs to understand when to help the learner and when to let them learn by themselves. So this third part about suggesting a curriculum for human motor learning is what I'm going to talk about in the third part of the talk. How should I act in a physical environment? How should a robot mediate in a scenario of intelligent disobedience? So we looked at the problem of human motor learning. And here you can see an example of a game called Kendama, where the person needs to put the ball inside a cup, like they just were able to do. And we wanted to see if we can train a person on this task faster than they would have if they just tried that on their own, using the robot that they are donning. This is a Harmony exoskeleton. So for that, we wanted to ask, how long does it take to master a skill like playing kendama or playing tennis or playing the piano? And there's a magic number that people usually refer to, which is the common rule of thumb for the number of hours you need to invest, which is 10,000 hours. But obviously, this can change a lot. It can be 10,000 hours, or it can potentially just be 500 hours. More than the number of hours, it is crucial, not the quantity, but the quality of training that we are providing. So that was our goal, how to train efficiently to promote learning. We don't care how long it takes, but what should the content of that training be? So this is what I'm investigating in this specific project. Can we construct an efficient curriculum that will help us master a skill faster? So while we don't know yet the exact mechanism of human learning, there are several theories that have tried to explain what goes on in the background, and many of them follow a recurring theme. So for example, challenge point theory is something used in motor learning, where they have a performance in practice curve, which means that the more you are expert in a task, you will need a more challenging task to improve. And you have some optimal challenge point that you should train in, and that changes with time. In pedagogy, there's a similar notion of scaffolding in which teachers should provide students with just the right amount of scaffolding to help them be able to solve the task, but for it to be challenging for them. And a similar concept is also from game design. This theory of flow channel says that any activity really is engaging if it is within the flow channel, which means that it is not too hard on the person, that it's frustrating, but it's also not too simple. So when we compare all of these theories and others, the common thread is that as the learner gains more expertise, their next best training tasks should change as well. So the curriculum should be dynamic to some extent. And we want to understand how to develop that. So we started by looking at how we train artificial agents before we train humans. How do artificial agents learn? We took a Markov decision process, for example, and an RL agent, a reinforcement learning agent, that learns from interactions with the environment. We have some actions that the agent can execute to get some reward, and the state changes. And we wanted to understand how can we optimize the policy of the agent so that the accumulated reward in the environment is maximized. How can we train this agent better? And the way that people have been looked at this problem was using a curriculum Markov decision process. So this is a type of a meta MDP. This is a work by Samit Narvekar and Peter Stone, where basically they designed this learning agent. It has some state of learning, it knows some things, and our task as the curriculum MDP is to offer the next training task so it can perform better. So that agent trains on the training task we gave it to it until we reach some target knowledge state, which is a threshold performance, or that it is able to reach some goal. So this is a meta MDP in which we can plan the next best step that we should give the agent to perform. Now we wanted to take this model and bring it back to human learning, but it's not straightforward. First, it's very easy to see that the skill state of an RL agent, we just look at the weights of the agent or its policy, and you can't look inside people's brain. And it is known from educational research that there are ways to trace knowledge, but we can't know that for sure. We also don't know the mapping, how one task would affect another. For example, if we're playing tennis, if we're practicing our overhand serve, will we also improve our underhand, or will it interfere somehow with one another? For example, if you are tennis players, then you might know that playing ping pong, seems to be like a good thing to practice, but actually it can mess up your tennis playing. So it actually interferes with one another. So we don't know this transfer, so it's very hard to plan if we don't know what's going to happen. And third, it's very easy to query the skill level of an RL agent. We just shut off learning. With people, we can't just have a switch and tell a person, you're now taking a test, but don't learn anything from it. So this is something we need to also take into consideration. So what we've done in this work, part of what we've done so far is to create a human skill curriculum MVP in which the actual state of the person, knowledge state is unknown, and we're using a set of metrics to estimate its current knowledge state. And in this belief state, we can now plan correctly for like how to optimize the behavior of the teacher. And if you're familiar with MDPs, then if CMDP is an MDP, basically you can say that this work is a type of a POMDP. If you're familiar with this line of work, then that would probably make sense. We tested that in two domains. One of them is Rich Ninja, in which we had this marker that the ball is controlling the red marker, and we're trying to capture blue markers. And we had the Kendama with the harmony task. And this project was running so far for 3 years. And we were able to find both intrinsic and extrinsic measures of skill in highly coupled human skeleton tasks to evaluate how well a person is able to perform a task and how skillful they are in that. We had 2 new platforms for dynamic human motor skill learning. And we got a promising result that the robot is not interfering with learning, which potentially when you have this huge robot on you, it might also interfere. So we verified that this is not the case. And we are now ready to set the grounds for curriculum learning approaches. So this is very exciting, this is ongoing, and hopefully again, I'll be able to tell you more soon. So if I summarize, why didn't the robot cross the street? Because it had a lot to take into consideration. It had to recognize a discrepancy between global and local objectives, or an inconsistency between the handler's plan and the objectives. It had to consider the proper remediation, that it will also maintain the objectives, but also promote trust through legibility and explainability. So it's a long work ahead as well. I'm very enthusiastic about disobedience. I argue that it requires informed agency. And some of the things that mean is that we need to understand the boundaries of our disobedient AI. We need to understand the teammates' knowledge and capabilities. We need to align the shared policies with both global and local objectives. And we need to be able to execute safe and trust promoting plans. I had a lot of collaborators on these lines of work that I've showed you, and I'm very happy with collaborations. I really like working with new people. I do hope that you reach out if you found something interesting, talk to me, so potentially I can put your face here as well for the next time I give this talk. Thank you so much, and if you have any questions, I'll be happy to take them.
Thank you so much, Professor Mirsky. That was a very interesting talk. I really enjoyed both all of the 3 topics. They're fascinating to me. Just making sure I'm on the screen as well. Do we have any questions? If you have any questions for the speaker, we have time for maybe 1 or 2 questions. You feel free to use the Q&A feature to ask your questions. And while I wait for that, maybe you can ask a quick question regarding the first part of the goal recognition problem. I'm curious to see, what happens if an optimal policy is not used, whether or not you can learn kind of the goal from the agent. More importantly, what if a deceptive strategy is used? What if the person is purposely trying to not get identified with their objective? Have you thought about that particular problem?
Yeah, so that's a very exciting angle on this work. So generally, there is some work on deceptive goal recognition. If you want, I recommend looking into Peter Master's work. But certainly, one of the benefits of using something that we've learned is that we can learn that from examples. So potentially, if the agent is intentionally deceptive, that might be more challenging. But if a person is just not optimal because people are biased that way or another, we can fit the policy to represent their behavior rather than some optimal learning process that we conducted. So potentially it can also estimate deceptions to some extent. The point with deceptions is that usually the point is to do something you don't expect, which is the exact opposite of goal recognition in a sense. Like they will try to break the system.
Absolutely. Thank you. I have a question here from Professor Odie. I think it's slide 12 or 13. There was a different relative performance decrease between the different colors.
This one?
Uh-huh. And the question is if you can provide any observation, even if anecdotal, about why the different colors had different performance decrease.
Yeah, so these are different techniques for measuring the behavior. I have a slide on that that I can pull up quickly. Yeah, so no, sorry, it's not this one. Infer. Yeah, so max util basically is just an accumulation of the Q values, if you're familiar with Q functions, of what the observations gave us, how good was the execution given the Q function that we have for each possible goal. KL divergence compared the observations as a policy to each potential policy for each goal. And convergence point is a different metric that we've developed based on some work that we've had so far. So these are three ways to measure, because you have a policy per goal and you have a sequence of observations, how to measure a linear sequence to a policy. So we had different metrics that we used here, and we had different performances with different approaches. Mainly the third one of convergence point was something that we were, it was more experimental and it did not perform as well. KL divergence and max util were very good in both cases.
Great, thank you so much. I think in the interest of time, I'm going to thank you again for the wonderful presentation.